Rice University. We talk about Donaldson and Thomas curve counts for Calabrese with threefolds and birational modifications.
Thanks a lot. Thanks, Matthew, for the invitation. It's really cool to be here. Yeah. So let me start with by giving some sort of an outline, mostly because I wasn't the first person to work on this stuff, and then so I want to just give attribution. I want to just name all the people involved in case I forget them right at the beginning. So okay, so so if X is Fabio threefolds, then there's this theory of Donaldson-Thomas invariants, which I'll describe in a second. These DP numbers of X. And so the kind of question I want to talk about today is the following. So if X and X prime are birational, so is there a relationship between the DT invariance of X and the DT invariance of X prime? So this is the question, and the answer is yes. And I'll describe an explicit formula. Let me mention so who's working on this problem? So first there was a paper by Hu and Lee who gave a formula in some particular case. Then there's work of Toda, and this work is super important. So without his work, mine probably would not exist. I can comment on the history if you really want, but so there's work of Toda, and somehow, some of the methods, okay, mentioned, right? And then there's some work on myself. So I think the method in here is very different from the methods in these two papers. These two papers are somewhat related. I think this is more like wall crossing. Well, I don't really have any wall crossing. I more have just somehow. So I feel like it's somewhat simpler. So let me see if I need to say. Oh yeah, okay. So so these are the people who worked on it. There's a generalization of this. Let me write it here. So there's a sort of a more general story where X prime is allowed to be a normopole. And I'm not sure if I'll have time to come to this, but the kind of idea is very similar. But here again, so this goes under the name of the Krapin resolution conjecture, which is still open. And the relevant people here are, so Jim Bryan is the one who made this conjecture, and there's a paper with Cadman and Young where they have some, an arsenal of computational techniques for that are very combinatorial to attack this problem. Then there's work of Bryan and Steinberg. Then I give some partial results. At some point I thought I had proved this conjecture, and I was really happy, and it turns out that I hadn't proved it. So I was super sad. And then there's a paper by Dusty Ross, which proves it in the toric case. And the proof is combinatorial, so somehow if you're like me, you don't feel like this is the correct proof, but it is a proof, so it's really cool. Okay, so, and let me mention the methods. So again, this is just to give some sort of an outline and you'll make sure I give credit. So there are mainly two inputs. One is derived categories. And mainly this is work of Bridgeland, or comes from work of Bridgeland. And then there's these Hall algebras, these motivic Hall algebras. And at least for the flavor of Hall algebras that I will use, the main name here is Joyce. Or perhaps Joyce and Song, and at the same time there was this big body of work by Kontsevich and Sobelman, but that is sort of more refined, and I won't use it. Okay, so this is still content free. There's no information on these boards, but there's just a bunch of names that are very relevant to what I'm going to talk about today. I just wanted to make sure I got out of them. I got them out. Yeah. Okay. Let me start by trying to motivate what these DT invariants. So let me explain what these DT invariants are and why you might care. So DT stands for Donaldson-Thomas. So the very naive idea is that I like to like count curves in X, where X is, for me, will be like a smooth and projective variety over the complex numbers, and it will be also more over Calabrese threefold. So one thing you could, you could do is to take the Hilbert scheme of X, of like curves. So what is this? This is a modular space parameterizing subschemes of X, where the dimension of C is at most 1. This is the same thing as a modular space of like projections. And I like this point of view better because it uses sheaves, and at some point no only use derived categories, and so this is like a better idea to consider this point of view. But this space breaks up into many components. So let me fix like some topological information. So let's fix a curve class and an integer. So I really should be considering this Hilbert scheme over here, which is parameterizing the quotients where the Chern character of O of C is 0, 0, beta, n. So basically here I'm saying that I'm going to consider this Hilbert scheme parameterizing things that are supported on a curve and the curve class. The corresponding curve class is this fixed beta, and then the Euler characteristic of the structure sheet is n.
I'm sorry, can you maybe write that? I don't know, I can't read what you wrote.
What is, is my handwriting awful? Or is it?
CH?
Oh yeah, this is the Chern character, CH.
Oh, sure.
Oh, sorry. It's like, I mean, this Hilbert scheme is written like this, has like many components. And I'm just saying that you should consider them like one at a time. And like you fix the information which is like constant in families, which doesn't vary in families. Okay. So the really naive thing you could do is you want to like try and count the points of this scheme. This doesn't make any sense because these schemes are typically not zero dimensional. So instead of saying counting, if this were a zero dimensional scheme, I could either say count the number of points, or I could say take the topological Euler characteristic of it. So it's not a very strong way to motivate it, but this is sort of the naive way to introduce these invariants, is just to say that the DT invariant of X of class beta and n is by definition the topological Euler characteristic of this modular space. Okay, so this will be like my definition of it. And what typically one does is one collects all these numbers into like a formal thing. So I let beta and n vary. I have this number here, where this guy is just some formal parameter. This is just a formal series in these numbers. This is not quite true. So what I just defined is what one might call like the naive DT invariants. And to get actual DT invariants, you need work of Kai-Baron, which I'll mention really briefly. Let me do it here. So there's work of Kai-Baron. So he does the following. So for any scheme M, he associates weighted Euler characteristic chi b of them. I'm not going to go into details of how this is defined, but I'll tell you two properties. So what is this? If M is smooth, dimension n, then the chi-barand of M is -1 to the dimension times the topological order characteristic of M. So it's one property. And the other property is that let me write it this way, it detects, so non-reduced structure. So, and then it's sort of deformation invariant. So for example, the chi-barand of 2 points is the same as the chi-barand of thickened point. So here I have that C cross C, and here I have C of epsilon. Then, so this thing is deformation invariant. So, I let these 2 points collide, and the chi-barand stays the same. Well, the topological order characteristic cannot do this, right? It doesn't know about the non-reduced structure. Well, this guy does. So it's way more refined. So here, really, when I write down DT invariant, I should really be rewriting the chi-barand of it. On the other hand, the results I'll talk about, they also make sense and are true for the topological order characteristics, or for the naive DT invariants. So if you don't really care about this story, then you can just take just take it to be like a talk about the order characteristics of these Hilbert schemes. So, yeah, okay.
Sorry, you mean your relation will be true no matter which DT you choose?
Exactly. Yeah. I could use both the DT naive or the actual DT. It'll be true.
So it's like a relation in motives.
Yeah. Sure. I mean, in some sense, it is. Are there any other questions? So okay, let me a brief digression. So far, I mean, what I've written down doesn't really depend on the fact that X was Calabrese or compact or whatever. I mean, this is just definition, so it makes sense anywhere. And then, Barron's thing makes sense for any scheme. I think a finite type over C, so it doesn't. So I could have taken any variety, but somehow there's a connection to the original work of Thomas, where these invariants were defined where the Calabrese assumption is necessary. So in case you care about this stuff, so let me see. So the original work of Thomas, was about moduli of, let's say stable sheaves. So the kind of thing you would consider is like ideal sheaves. So you take like the moduli of sheaves here with Turing character, stable sheaves with Turing character 1, 0, minus beta n. And so this is the kind of modulus you would consider instead of the Hilbert scheme. And if you study the deformation theory of this, you get what is called a symmetric perfect obstruction theory, which, if you know about Gromov-Witten invariants, this is the kind of thing these are the kind of words you throw in to define these virtual classes and then the Gromov-Witten numbers. So you have one of these things, and one of these things buys you a virtual fundamental class. So more concretely, what happens is that you study the deformation theory of the space, and the Calabrese condition ensures this symmetric word, and this gives you that this virtual class is a zero cycle. So this is where the Calabrese condition comes in. So you have this virtual fundamental class is a zero cycle, and basically what Barron proved is that the degree of this is the same as its chi-barand. So in the case when your moduli space has one of these symmetric perfect function theories, then I could take the chi-variant of it, or I could take the degree of its virtual class, and I get the same thing. So this is where so the original approach was about moduli of sheaves. Somehow, for the kind of techniques I want to use, I prefer to use the Hilbert scheme. And but they're equivalent because of this work of Barrett. I can just use this definition of the chi-variant. By the way, I should mention that a good reference for curve counting in general is this paper, 13.5 ways to count curves. By Pandaripanda and Thomas. There's an overview of many counting theories, including Grove-Witten theory and Bouncing Time theory. The other digression I want to make before I state my theorem is the following. So there's a relation, which I won't really mention, with Grove-Witten theory. I mean, I'm mentioning now, but I'm not explaining it in detail. So there's a relationship with this theory. So, and this is due. There were some conjectures by Malik, Necrosso, Punkov, and again, Pandaripanda. And so, which basically says that from the Grove-Witten theory, you can recover the Thompson-Thomas theory. So there's like an explicit formula to go from this theory to the other and back. And this has been proved basically for almost all Calabrese threefolds. Almost all three by Pandaripanda and Pixton. And it's kind of surprising that there's a relationship between these two theories. So maybe just to remind you briefly, just to see the difference in flavor. So somehow,
I'm sorry, is
Yeah.
this something new?
what is?
But Grepal Dixon,
What does new mean?
like last year?
Maybe 2 years ago? I don't remember exactly. Yeah.
Because originally I thought they only proved it for torics.
Yeah, that's why I say almost. Yeah. Almost all Calabrese threefolds. So they have, no, but it's just, I think it's more than toric because they have some degeneration formulas, so they can leverage it to, I think they could prove more than just toric. That was
The
my
original
impression.
one was Molik, Okonkov, and Pandaripanda, right? So this is at least a new statement, but so what is also?
Yeah, I don't remember the exact statement, so we can look it up in the. I think they have more than one paper on this, and so it's definitely toric, but they can also. I think they can also degenerate somehow. I don't. Yeah. Yeah, this is really way above my pay grade. So, but yeah, so they originally conjectured it, but did not prove it. But but then they could actually prove it in many cases. Let me say it this way. So somehow 8th grade, but these two theories are of a very different flavor. So, and then, in Grove-Witten land, what you're doing is that you have your x, and then you have your curves, which are like stable curves, and you map it into x. And somehow in this theory, you're allowed to collapse. These are what are called stable maps. So Grove-Witten theory is really a theory about maps. But you're sometimes allowed to contract components. So somehow in this Grove-Witten theory, the maps aren't great, but the curves themselves that you're trying to count are very good. Because they're these like stable curves or synodal. And on the other hand, in Donaldson-Thomas theory, what you're doing is you're looking at the Hilbert scheme. So you're looking at really subschemes of X that have possibly non-rigid structure, and you're also looking at points because it was the Hilbert scheme of dimension at most 1. So you're looking also curves that might have embedded points, and these points can float around, and it's really remarkable that there's a relationship between these two things at all. So somehow in DT theory the situation is completely reversed. The maps are awesome. They're the best thing ever. There's some embeddings, the subscheme, but the curves are as horrible as they can be. Anyway, so. Okay, so this is sort of my introduction, and apologies if it was a little bit too vague, but now I'm going to get to something which is more concrete. Do you have any questions? Okay. So let me go back to the question we want to ask. So now we have these dt numbers, which are defined in terms of this weighted Euler characteristic of the Hilbert scheme, and we can ask the following question. So if so y will be Flavio threefold, which means for me will mean so smooth and projective of the complex numbers will be of dimension 3, and the canonical bundle of y is trivial, and also h1 y is 0. Okay, so the question is, if y and say w are birational, so again, is there a relationship between the dt invariance of y and the dt invariance of w? So this is the question I want to answer. And again, if you don't care about the dt invariance, you might care about the Euler characteristics of the Hilbert schemes. So I'm going to give some kind of relationship between these Euler characteristics. So first of all, there's a general fact in birational geometry. I guess the general theorem is due to Kawamata. I think, just for the case I want, I think it might have been by Kolar before this. But anyways, the point is that, so y and w are birational, they're both Calabrese threefolds. So such a thing is, so if you give me a birational equivalence between y and w, I have that y and w are connected by a chain of flops. Okay. So basically all I'm saying here is that if I want to study a general birational transformation, I can just reduce to the case of flops, which are which is a specific kind of birational transformation. So what I'm going to do now is that I'm going to say, okay, so I'll give you an explicit formula in the case of flops. And let me remind you about this thing. So the relevant picture is the following. So something I have like y, like x. So I start with y here, and in the simplest case I have like a P1, a rational curve instead of y, and I'm contracting this curve to some singular point inside this some other variety x, and then I'm resolving it in a different way. So I'll have a diagram like this with two Claudian threefolds y and w that are both mapping to the same space x, and they're contracting this rational curve. And so these two guys are birational. They're isomorphic away from a codimension 2 subset, so they have the same divisors. So I can really, so they have the same divisors, and so they'll have the same curve classes. So now it makes more sense to I can have it's more, I mean, it's more rigorous. Now the relationship between these two things has a chance of having a meaning, because I can relate the curve classes. And this guy's called a flop. Basically, whenever you have a divisor which is intercepting like positively this curve, I take the proper transform of it. It's going to intersect this guy negatively. But I don't want to spend too much time on this, because I'll give you a different perspective on flops using these derived categories. But let me just write down. So basically what I'm saying here is that, so if phi is one of these flops, I'll have an identification to have phi star, which is like the proper transform on divisors, but I can also interpret it as being a proper transform between the curve classes. And so now it makes sense to write write something like this. So Donaldson, I can like transport this series from one side to the other. Right? Does this make sense? So basically, all I'm doing is that I'm taking this formal variable q beta n, and I'm just sending it to q. I'm just taking the transform of this curve class and then just leaving n alone. Okay. So now I can actually relate the invariance on this side and invariance on the other side. And so the actual theorem is the following. And I should put it here myself. So if y and w are now related by a flop, okay, then I need just one extra definition, which is the following. So let me define dt. I'll define dt exceptional of y to be the same thing. So I'll just take the formal series of all dt invariants, but I'm only considering the classes which are contracted by f. Okay. So remember, I had these dt invariants which are each individual term is defined in terms of the Euler characteristic of the corresponding Hilbert scheme. And I assembled them all together into this like formal series, which is like dt of y. Now I'm considering only the terms that are contracted by f. So basically, in this case, I would just be considering things that are the curve classes, which are like multiples of this curve. Okay. Now I need to do a funny thing, which is I'll introduce this like sign change over here, but this is no problem at all. Okay. So I'll consider this thing, and now the claim is the following: is that when I take the transform of this product, then I get the same thing on the other side. Okay, so this is the claim. So, I mean, in general, for general rational transformation, maybe it's not so clear what happens, but by this general theorem, I can break down any rational modification into a chain of flops, into a finite sequence of flops. And for each flop, I know exactly what is going on. It's this thing over here. So this this formal series of all these Euler characteristics is going to transform according to this rule. Yeah, are there any questions on this? Okay. So now I want to try and tell you a little bit of, how you can actually prove such a thing. Okay. So, right. So these are the invariants were defined in terms of the Hilbert scheme. So the goal here would be to try and relate. So I want to relate the Hilbert scheme on y. I want to find some kind of relationship with the Hilbert scheme on w. But it's not very clear how you do it, and these whole algebras are where it comes to the rescue. So first of all, there's this theorem by Bridgeland, which is the first step in all this. So in this case, where a y and w are related by a flop, then what I have is that the derived category of y, and by this I mean the bounded coherent derived category of y, is equivalent to the derived category of w. So this is already, it's a first step, but it's still not telling me enough. But I mean, somehow, at least I know that the sheaves on w are closely related to the sheaves on y. But actually, Bridgeland tells me way more than this. So let me see. So one thing is that there's a heart of a T structure, which is called which he called the category of perverse coherent sheaves inside of d of y. And what happens is that the equivalence sends this category, this heart on one side with this other heart on the other side. Now this is a small lie, because actually there's a whole family of these categories indexed by the integers. And what happens is that they'd all get shifted by 1. But whatever, for the purpose of this talk, it's not super important. Not only this, but he also tells you, so this is somehow, I'm going to write down the definition of this guy in a second, because it's really not complicated at all. And it's purely intrinsic to the map from y to x. And he also realizes, W as a moduli space of point-like objects. Let me say point-like perverse coherent sheaves. So somehow it doesn't really matter what the flop is, what the flop W is. What I need to know is this map over here, and then I can just consider this category here, which is intrinsic to Y, and take this moduli space, and this will be the flop. This is like a, yeah. Okay. So I assume I don't need to remind people what the derived category is, but if not, I can do it briefly. I guess so. Okay. But basically, I won't be trying to explain anything deep. The thing is, this guy's the heart of a T-structure. What does this mean? This is an abelian category. So we can talk about exact sequences in here. And exact sequences in here are sent to exact triangles in here. So this is, the prototype of such a thing is coherent sheaves sitting inside here, and this is like another guy, which satisfies the same kind of axiomatics. So let me write down this definition of this category. So by definition, this guy is the following. So these are all complexes in D of Y, such that, so let's see. So if I take the cohomology sheaf, so so these are chain complexes of coherent sheaf, so this is some coherent sheaf. This is 0 for I different from -1 and 0. Then I have the following thing, that if I take the push forward of H minus 1 of E, this is 0. And if I take the R1 of F lower star of H0 of E, this is 0. So this is really all there is. These are just two-term complexes that have this property. So again, we had this y over here, and this p1. This is curve C. And f. So basically, whenever, if t is a coherent sheaf on y, and the support of t is disjoint from t, then t belongs to this category. Also, the structure sheaf belongs to this category. What happens is, an example of something that doesn't belong to this category is something like OC minus 2. So this doesn't belong to this category, but if I shift it by 1, right, this will be one of these guys. And so this guy belongs to this category. Basically what happens is that, so I don't want to get into too many details, but what happens is that if you take the skyscraper, but as I said here, if something is supported outside of C, then it lies in this category. So I take the skyscrapers here, and they all lie in this category over here. But as soon as I hit this curve, then they stop living in this category. Well, no, they still live in this category, but somehow they're not a quotient of the structure sheaf anymore. And so what happens is that what happens is that when you take the limit of a skyscraper approaching here, you get a different quotient, and this corresponds to a skyscraper on the curve on the flop. So this is how this the flop is really a moduli space of these like point-like objects, because somehow Yeah. Basically saying that the map from OY to the skyscraper sheep is a surjection in this category. When you're outside of the curve, that's fine. But when you're on the curve, this is false. And so you have to replace it by some other like point-like perverse coherent sheep, which corresponds to a skyscraper on the other side. Yeah. Okay. So let me go back to the question. So as I said before, the goal would be to somehow relate the Hilbert scheme on Y with the Hilbert scheme on W. From this equivalence, though, we can do something which, a priori is completely unrelated, but it's not. So the structure sheaf on Y is one of these perverse coherent guys. So I can consider this moduli space over here, which is a moduli space of maps like this, where E is in this thing, and we'll call this S. S is an epimorphism in this category. So this modular space makes perfect sense. And the Berzon's equivalence, so I should mention the equivalence is also sends the structure sheaf on Y to the structure sheaf on W. So really what we know automatically is that the equivalence will identify these sort of perverse Hilbert schemes. So let me write it. So Berzon is telling me that the perverse Hilbert scheme on Y is the same as this perverse Hilbert scheme on W. Okay, so this is really good. So it really looks like we're in business. So again, what I'm trying to do is I'm trying to understand how these DT invariants change from Y to W, in this case of the flop. And I have this theorem that is telling me not only that the derived categories of Y and W are the same, but also this more refined information about the T structure, about these perverse coherent sheets. And just by looking at this definition about what it is, I can do some properties. I have these moduli spaces, and they're isomorphic directly from that equivalence. So now the goal is to relate. The idea now is that I want to relate the chi-barand of this P node with the chi-barand or the ordinary Euler characteristic with the ordinary Hilbert scheme. And this is where these Hall algebras come in. How much time do I have? When do we stop at 30 past?
Yeah, 20 more minutes.
Okay. So, are there any questions? Right. So here's where I need to talk about these Hall algebras. Okay, so first of all, there's this thing called the Grothendieck-ring of varieties, which is the following thing. So it's the free-reading group generated by varieties, elevated like this, X, subject to the relation which say that the class of a variety X is the same as the class of the variety Y class complement for Y closed subvariety of X. Okay, so there's this, and this is a very interesting ring, and there's many questions one can ask about it, but so right, whereas the ring structure is coming from the product of varieties, but we won't really need it. Okay, so I can do like a relative version of this thing. So I can fix base S, and I can consider the following thing. Variety over S, and it's the same thing, only that it's going to be generated by maps from X to S. And now the relations are the same, or pretty much the same. So if y inside of x is closed, then the class of x goes to s is the same as the class of y goes to x goes to s, plus the class of x minus y goes to s, goes to x. Okay, so again, it's exactly the same thing, well, it's relative over some base. Now suppose I have, so let me see, so I want the diagram of this form. Let me call this T. So suppose I have any diagram of this form like this. I can endow this guy with a product in the following way. So I'm given something like this. What happens is that I'll do the following thing. If I start with two maps like this, we call this F, G, I can take them F comma G. And what I can do is I can take the fiber product of this thing, this will be from Z, and I can take the composition. And this is what I'll call that convolution G. So given two classes like this, I can form their convolution, which is given by this composition over here. And now, if I pick this diagram at random, this doesn't have to satisfy any good properties, but I'll give you an example now where it's actually you get an associative product. Right? So what I need to do is I'm going to have to replace varieties with stacks. And S will be the stack of coherent sheaves on my Fabio threefold Y. And now my T will be the stack of short exact sequences. And these two maps do the following thing. So let me write it here. So there's the map that goes over here, sends a short exact sequence like this. To the pair A comma G. And the other map, A comma C. And the other map will send it to B. Okay. So basically, all I'm trying to inject into this growth-deep ring of varieties over the stack of coherent sheaf some information about somehow the homological algebra of this category. Some categorical information, some information about the exact sequences. So at the end of the day, I'm concerned with the Hilbert scheme. And the Hilbert scheme is a moduli space of like epimorphisms in some part of a T structure. And so I want some information in this ring. So just to and there's two basic identities that I want to play with. So let me call this. So this is the growth-deep ring of the. So sorry, I didn't say what the Hall algebra is. So the Hall algebra is this thing. It's the growth-deep ring of stacks over this moduli, where S is the moduli of coherent sheaves on Y. And the star over here is this convolution that I defined earlier by doing this pull-push thing with this map having to do with the short exact sequences. So there's two identities here that are kind of important. So if I have one of these things called a torsion pair, so basically if I have something like this, so if I have two categories like this, and go and F and go, such that for any coherent sheaf, there exists a unique short exact sequence, like so, with T and T, and F. So this, for example, you can take actual torsion sheaves and actually torsion-free sheaves. And this is like the prototype of a torsion pair on a category. So if but even think about like in terms of modules of abelian groups. I can take like the torsion part of the abelian group, and I can take the quotient, and this is like what is left is torsion-free. And this is like the prototype of a torsion pair on a category. So it's something like this. So I can consider these elements in the whole number. I can consider this element, I'll call it 1 co, which is corresponding. Oh man, I should have written this as co. Sorry. Like this is really the stack of coherent sheaves. So what I mean here is I have the identity from coherent sheaves to coherent sheaves. Then I have this thing, which is just the inclusion of this moduli stack inside of here. This is identity. And what I have is that from this property here, from the fact that I have, there exists a unique short exact sequence like this, and the definition of this product, which has to do with short exact sequences, I have the following identity. So basically, okay, so if I've lost you, the whole point of this ring, of this Hall algebra, is that I'm trying to encode some categorical identities about this category into identities in this ring. So I have some category theory fact, which is this thing. So any sheaf can be broken up into a torsion sheaf and a torsion-free sheaf. Is encoded in this identity over here. So, and this is a really cool idea. So I mean, this is something purely in category theory, and this is something in a ring. Now, let me write this. I also have an element corresponding to the Hilbert scheme, which is, well, the Hilbert scheme is what? Let me write it here. So this is the map from here to here. So the Hilbert scheme is a moduli of surjections, and here I just map it to OC. So I just forget the section. I just remember that with the sheet. And I have another guy here, which is this guy, which this is, I'll take the moduli of So I have another element here, which is considering the moduli space of a sheaf equipped with a section, which isn't necessarily a surjection. So I have the moduli space of like sheaf with a section, and I can forget the section, and I'll land into my stack of coherent sheaves. So here I've done a similar thing, but I had a surjection. Here I don't have a surjection. And basically, the first isomorphism theorem for coherent sheaves can be translated into this other identity. Let me see. So. So this is basically saying that if I have any morphism like this, I can factor it into a surjection composed with an injection. I take the co-kernel of this injection, I get this other guy over here. But basically, okay, this is obviously too fast, but the point is that the first isomorphism theorem translates into an identity in this ring, in this Hall algebra. And I guess I'm running out of time. But the point is that these two identities are pretty much all we need to do this to get the theorem we want. So let me just try and explain this briefly. so remember, we wanted to compute this thing, we wanted to relate the DT invariance on Y and W, and Y and W are related by this plot. And what we had was that the perverse Hilbert scheme on Y was equal to the perverse Hilbert scheme on W. And this was due to this thing by Bridgeland. And so now we want to relate the perverse Hilbert scheme, or its invariance, with the ordinary Hilbert scheme. And so I'll do a similar discussion using these kind of identities, not with the stack of coherent sheaves, but with the stack of these perverse coherent sheaves. And basically, I have these two categories I have these two categories in. I have this thing, right? Which, well, let me do it this way. So I have A, which is the perverse coherent sheaves intersected with co, and then I have B, which are the perverse coherent sheaves intersected with co shifted by 1. And it turns out that this is a torsion pair. In this category over here. So in this Hall algebra, I'll get an identity like this. And yeah, I don't think I have time to explain this very well. So basically, I have this torsion pair, and then I have other similar identities using this. Well, let me see if I can explain. Yeah, okay, maybe I can say the following thing, or at least give you an idea of why these two things should be related. So this is the guy we wanted to consider, and this was the moduli space of maps like this, which were epi in this category here. So this means that I have in this so this is an exact triangle in the derived category, and the claim is that all of these are in this category. So for this to be an epimorphism in this category, this means that if I take the cone of this, or the cone shifted, which is this guy, then all three of them lie in the heart. This is what it means for this guy to be an epimorphism. So I can look at what happens in cohomology, and what I get here is that I'll have h minus 1 of E, so some guy, h minus 1 of E, no, sorry, what? Sorry, okay, I have h, the point is that from an exact triangle like this, I can look in cohomology and I'll get a map from O to Y to H0 of B. And this map has to be a surjection, right? Because, I mean, these were perverse coherent sheaves, so they were concentrated in degrees only -1 and 0. So basically, given one of these, one element here in this perverse Hilbert scheme, I can pass through cohomology and I'll get an element in the ordinary Hilbert scheme. And this really, since I'm using cohomology here, it really looks something that I could possibly translate into this Hall algebra, because it's sort of an identity which has to do with like kernels, co-kernels, and short exact sequences, or exact triangles. So this is really what happens. I can break up this element here in the Hall algebra in terms of the Hilbert scheme and some other stuff. And the other stuff is what contributed to this dt with this change of signs, and then the Hilbert scheme is what contributes to the dt invariance. So this is how I get the formula in the end. Yeah, okay, I think I'll stop here. So,
Any questions?
yeah, sorry if the end was a bit rushed. Yeah.
Any questions? What happens if you take other classes of binational transformations?
What do you mean?
Like not flop, but something else. Do you have some similar relation?
Well, not really. I mean, the thing is, no, the thing is with the flop, I have this really explicit way of relating these two things with the T structure. In general, I'd have to start with the Brownian transformation, composing, breaking it up into a series of flops, and then seeing what happens. But then, I mean, as soon as I compose two, it's probably going to get way more complicated.
So this was really tied up to dimension 3 and simple flops. The conjecture is possibly true in any dimension, right? So,
In any dimension.
yeah.
No, I mean, this conjecture about these DT curve counting events is really about threefolds.
No, that one, yeah, the D equivalence equals K equivalence conjecture is in any dimension, right?
Oh, yeah, sure.
And we don't have an analog of the DT theory,
Yeah.
but we do have well-defined moduli spaces and everything there. So these relations that you are writing for, say, moduli of perverse coherent sheaves, they should make sense in the Grothendieck group of varieties, for moduli of any dimension. And in clue of what's happening, I mean, I guess it's an elaboration on Marcy's question. What if the flop is not a simple, in higher dimensions, you won't be able to decompose anything into a sequence of simple flops, right? So,
Well, I mean, the fact that the flop is not simple is maybe, so the real problem, the real problem here is that I can definitely work with things that contract a curve to a point, or many curves. It doesn't matter how many curves are here. But the point is that the relative dimension has to be 1, but also the dimension of this guy has to be 1. As soon as this guy is in the threefold case, as soon as this thing is like a divisor contracting a curve, this is this thing I was mentioning at the beginning with this Kreppen resolution conjecture of Brian, Cadman, and Young. And there are problems. Basically, the fact that this is of dimension 2 breaks down these identities. Not this one, I mean, I haven't written down the crucial one, but there are some identities that has to do with like, basically like skyscrapers are not having, H1. It's things like this that complicate matters considerably. I mean, it's, maybe I can write down this. I can consider this guy, which is again, so I'm considering the moduli of, and I'm sending it to this stack over here. So I'm considering the moduli space of like a perverse current sheaf and a section. And what I would like is something like this. I would like an identity like this. And certainly in this case, this holds. And basically this has to do with the fact that if I write down the point is this, is if I write down an E like this, and it has a map here, I have this short exact sequence like this. And basically when I look at the long exact sequence for Hom from O to this, I get a short exact sequence. But if this weren't one-dimensional, I would get a term like following here, and I can't get rid of that if I had something of a higher dimension here. So it's really tricky. There's something somehow. I mean, sometimes there's something derived going on, but I wouldn't know how to. I've thought about this for a long time. I don't know how to translate into an identity in the Hom algebra. I mean, maybe you need like this Toan higher algebra type thing, but I higher like Hom algebra, derived Hom algebra, sorry, but I'm not sure that would help. I'm not sure.
Is it possible that the Hilbert W and the Hilbert Y is just a change of stability condition in the same derived category?
Yeah, so this is the kind of approach that Toda uses. So so he uses like this notion of weak stability condition, so he can bypass all the problem of like stability conditions on Calabrese threefolds not being. I mean, especially at the time when he wrote the paper, it wasn't clear whether you had any stability conditions on the whole category. So he has these weak stability conditions constructed in some special subcategories, and in some sense, yeah, it is. There's a wall crossing formula, and you can go from like one chamber of the stability space to the other, and he passes from one moduli space to the other. So there's a way to like change the stability condition and get from one thing to the other.
And then in that case, the wall crossing formula is the same as your formula.
Yeah. So you get the same formula, sure. Yeah.
Let's thank you, the speaker again.